Hello, and welcome to Experiment 9, Gas Laws. As always, I got my lab coat on, I got my safety goggles on, and I'm choosing not to wear gloves, but that's an educated choice on my part. You can absolutely make your own educated choice about whether you would like to wear gloves or not for this experiment. We are exploring several of the gas laws, the individual gas laws that you should have discussed in class. We're only going to look at two of them, the relationship between pressure and volume, which is Boyles Law, and we're going to look at the relationship between pressure and temperature, which is Gay-Lussac's law. Now, I personally am not in favor of memorizing whose law is whose, because all of them get squished together in the combined or ideal gas law, where pressure times volume equals number of moles times a constant times temperature. And since PV equals nRT, if you do a little rearranging, you see that PV over NT equals a constant. Pressure times volume divided by number of moles times temperature equals a constant, which means that if you have some starting set of conditions, PV, N, and T, and that will equal some final set of conditions, PV over NT. And if you don't change some of those variables, let's say we don't change the number of moles of gas, then we would have PV over T at the beginning equals PV over T at the end, because the number of moles doesn't change. If we also don't change the temperature, then we would have PV at the beginning, P times V at the beginning, equals P times V at the end, which is Boyles Law. If we didn't change the pressure, if we didn't change the number of moles and we didn't change the volume, then we would just have P over T at the beginning equals P over T at the end, which is Gay-Lussac's law. And so we're going to look at a couple of those. We're not going to look at Avogadro's law, although I'm sure you'll agree that if I have no amount of gas in this syringe, and then I suck some gas into the syringe, that now there is more gas in there and it takes up more space, which is the genius of Avogadro's law. No experiment necessary. If you have more gas, it takes up more space. Not too challenging. We're also not going to look at Charles's law, volume and temperature, although maybe at the end of the experiment I'll just slam this syringe into the hot water and see what happens, if there'll be enough temperature change to cause the syringe to expand, to blow up. We'll check it out. So, first thing we're going to look at is examination of pressure and volume, which is Boyles' law. And to do that, we're going to get our old pal, the temperature LabQuest sensor here, which will also, depending on what we have plugged into it, measure pressure. So, turn it on. And it, as always, knows what we have hooked up to it. And so it's reading a pressure in kilopascals, which is the SI unit and the default, and temperature in degrees Celsius. Now, interesting point. Changing from kilopascals to millimeters of mercury or atmospheres or torr is just a multiplication or a division. And since our equation is a multiplication and a division, we would be multiplying this kPa by the same thing on both sides. And so we don't technically have to do it, but I can change it by clicking on change units, and we'll go to millimeters of mercury because that's what's most common for us when we are discussing this in class. Now, I could change this to Kelvin if I wanted to, but again, there's not really a reason to do so. Take it. Because we're just looking qualitatively here. We're not doing any sort of quantitative analysis. So we're just looking what happens when the temperature goes up, what happens when the temperature goes down to the pressure. What happens, we could do it the other way. We could change the pressure and see what happens to the temperature, but that's not the experiment that we're going to do. So I went ahead and I did change the display into units that are more common for us in our discussions in the class, but you could absolutely leave it in degrees Celsius if you want to. It's just up to you to decide what are you going to record on your data sheet. Okay? So right now, with nothing hooked up to our pressure sensor, move my temperature sensor out of the way, you can see that we have 753.3 millimeters of mercury. And so that is what our reading is if I just hook up my syringe to it. The sections on pressure and temperature sensor calibration, calibration of the temperature sensor, and calibration of the pressure sensor, none of those sections are necessary because this is self-calibrated. So we're just going to go straight into step number 1 of examination of pressure versus volume, which is set the syringe to be half of its volume. This is a 5 milliliter syringe, so we'll set it at right at 2.5 milliliters. 2.5 milliliters. And the pressure sensor is threaded. We'll make sure that it's on there tightly, this adapter. And the syringe is also threaded, so we can just screw it on. And so right now, our pressure sensor is reading really close to 1 atmosphere, 760 millimeters of mercury. Right now we're at 759.9. Ooh, there we go, 760. I haven't done anything to my syringe, right? I just threaded it on. So the pressure of the gas inside my syringe is the same as my pressure in the room. And then it says, set program up to read and plot pressure, which we already have set up, and start the program to collect the data. So we just press the green button in the corner to start collecting data. Okay? And then I will let you see, as I press this to half of its volume, so I'm going down to 1.25 milliliters, we'll see what happens to get the light properly. Just hit my exposure there. You'll see what happens as I squash the syringe now. I'm down at 1.25, and you can see that the red line has gone way up. The pressure increased when I decreased my volume. Volume down, pressure went up. Now I'll let it back to its original 2.5 milliliters. And you can see that our pressure went back to atmospheric pressure. Now, so long as I don't have any leaks, I'm going to try and expand this from 2.5 milliliters to 5 milliliters. And look at that. The pressure dropped. When my volume got bigger, my pressure got smaller. So we seem to have what is known as an inverse relationship between pressure and volume. When the pressure went down when my volume went up, and my pressure went up when my volume went down. So now, if we go to stop our run, we could have just read the numbers off of the screen here, the pressure numbers. But if we go stop our run and then change to change our reading, instead of the graph, we put it into the data mode. If on the side, on our screen here, we go to XY in the corner, then we can see we started at 751.4 millimeters of mercury, and when we lowered our volume, we got up to somewhere in the order of 1493. And then when we decreased our volume, we got all the way up to, 1736 is where we finally leveled out. Scrolling through our data, went back to atmospheric pressure, and then we halved our, we doubled our volume, and we got to like 418 millimeters of mercury. 418 millimeters of mercury. And then back to atmospheric pressure at the end. So it's up to you. You can ask your instructor if they're going to want you to graph all of these data points. You could export this to a USB and to a computer and plot it all. But really what we're looking for here is not so much your graphing abilities, but our qualitative study of what happens when we change the volume. When the volume goes down, what happens to the pressure? When our volume goes up, what happens to the pressure? What is the relationship between pressure and volume? That is Boyles Law. Next up, Gay-Lussac's law, exploring the relationship between pressure and temperature. So we will disconnect our syringe from our gas pressure sensor. Set that aside, I'm not going to need it right now. We will take our vernier interface and put it back into the graph mode, just so we can see. We can always switch back and forth if we want to. And it's ready for the next run. We would just do run 2 there. And we're going to get a small dropper made out of glass or Pyrex, and we've sealed it at one end with a stopper. The other end is open, and we're going to connect it to a hose, piece of hose, that has a fitting on the end that will screw on to our gas sensor. Making sure not to rip the fitting off of the gas sensor. We could screw this directly into the sensor and remove the valve, but why not? We'll just leave it out. And then we're going to jam our dropper into the end of the hose. And now what we have done is we have made a fixed volume. Okay? Getting this hose to blow up like a balloon would take a lot of pressure change, and we're not going to do that radical of change. So this is a constant volume. So that what we can do is change the temperature of this glass by putting it in ice or putting it in hot water and see what happens to the pressure. So we're not changing the amount of gas in here, just like we didn't change the amount of gas in part 1 when we adjusted the syringe, right? The syringe was attached to the gas pressure sensor, and so when we squished the gas, we were literally squishing the gas. We weren't changing the amount of gas in there. And when we expanded the gas, we were literally providing more volume for the gas to be in. We weren't changing the amount of gas, because this was, again, hooked up to the gas pressure sensor. So we didn't change the temperature in part 1, and we didn't change the number of moles in part 1. They were constant. So PV over NT equals PV over NT. We didn't change N and T. So it was just PV equals PV. Now, in part 2, we're not changing the number of moles of gas, so N is constant, and we're also not changing the volume. So PV over NT equals PV over NT beginning and end, but we're not changing N and we're not changing V. So we have P over T equals P over T. And we're examining that relationship. Now, if you're good with your algebra, then you realize that when you have PV equals PV, if your two variables are on the same side of the equation, right, P and V are on the same side of the equation, that's going to be an inverse relationship. When we have P over T equals P over T, beginning and end, they're you know, above and below each other on if you're looking at the same side of the equation. We'll prove that in this part of the experiment. So what I'm going to do is slightly change the procedure. I have a beaker, a 100 milliliter beaker with around 60 milliliters of water in it. And I'm going to submerge my dropper into it. I am also going to then change the temperature by putting it in ice and putting it on a hot plate. Now you can't, an ice bath is not just ice in a beaker, okay, because we're not going to get enough surface area contact with the ice cubes. So you need some water to make a true ice bath. Okay, so now I have ice water, and the water will be at the temperature of the ice will be at the temperature of the water, and we'll have a nice cold environment to put our beaker into. I am going to get a temperature probe, which is already hooked up to my LabQuest, and I'm going to rubber band it right onto my stoppered dropper. Okay? And now I'll be able to dunk this guy in there. Now we got to be really careful, okay? We don't want any of our hoses, any of our power cords, any of anything to contact the hot plate when it's hot. Yeah, all right? So I'm going to put my LabQuest back into graph mode just so I can visually see it, but I'll be able to get my data later. And I'm going to hit go. We'll overwrite the last run. Yeah, that's fine. I can discard my data. All right, so I'm reading temperature and pressure. And if you can see right now, the pressure is 751, really close to atmospheric pressure. And my temperature is 296 Kelvin, right? I will submerge in my room temperature water, and we're getting no changes so far to our graph, but I'm going to now put my beaker into my ice bath. And you can see that the temperature is dropping. And my pressure is dropping, but only minimally so far. We're at 750.5, we were at 750.9, and we're dropping. Temperature dropping. My temperature is now at 288. You don't need to record these as I'm saying them because we will just go to the XY graph and print it or copy it onto our data sheet. My pressure is now down at 748. So it's not a dramatic drop, but if we changed our XY axis on our graph, you would definitely be able to see it for sure. Change our y-axis. So our temperature is down at 286, and our pressure is now at 747.9. Still dropping. So every time the temperature goes down, our pressure also seems to go down. Maybe I'll let go of the temperature sensor, not a bad idea to hold the temperature sensor and the hose more up here rather than having my finger on the temperature sensor. Our temperature is now at 283.6 and our pressure has dropped to 746.6. We're a little over 2 minutes. At 3 minutes, I'm just going to say we've seen enough, and I'm going to switch to the hot plate. Oh, looks like our run stopped at 3 minutes. I did not check my time of my run on here, so I should have done so. All right, so I have 3 minutes, and our temperature has dropped down to 296, and our pressure has dropped to 751. Now I'm going to switch onto the hot plate, and I'm just going to crank the hot plate to super hot. I'm going to carefully drape my power cord and my other cords over a clamp attached to my hot plate. I'm going to put these other cords also draped over the sink so that I don't burn anything. And I'm going to hit run again. If you've set your time properly, which I didn't, then you can just, your time will continue to run throughout the experiment. I'm just going to start again. I will just append my data this time. And we'll see what happens. I'll bring it a little closer. Okay, so I've cranked my hot plate to the maximum. My temperature probe and my fixed volume dropper are in the beaker, not touching the bottom of the beaker. My hoses are draped over a clamp that I have set up underneath the hot plate, and I've draped the hoses over the sink as well before I come back to my vernier interface. And you can see now our temperature is 284 and our pressure is at 744. And we will see what happens to our pressure as our temperature starts to go back up. The water is starting to sizzle on the hot plate. You may hear that. Hopefully this hot plate is somewhat clean so I don't have to inhale nastiness. And now you can see our temperature is dramatically increasing. We're at 290 Kelvin. And our pressure is also dramatically increasing. We're at 750. Roughly. Again, we will just switch this into XY mode and copy some of the data points onto, some or all of the data points onto our data sheet. But I think you can see already the qualitative relationship. What happens when the temperature goes down to the pressure? What happens when the temperature goes up to the pressure? Our temperature is now at 300 Kelvin. So our water is passing room temperature. And our pressure is at 750. Oh, did we time out? We timed out again. I'm just going to hit go again. I really should have changed the time. Append. Our temperature is at 306 and our pressure is at 761. So I've changed the procedure slightly from the lab manual. I started in the ice. I neglected to set my time, but I should have set it for longer. 300 seconds or 600 seconds would have been great. And once my temperature had dropped significantly in the ice, and I saw what happened to the pressure, I switched over to the hot plate, then turned the hot plate on full blast, and I'm watching what happens to my pressure as my temperature increases. I think we've probably got enough data at this point so that you can tell me what happens to pressure when we change the temperature, but we'll let it go a few more seconds. Temperature is currently 325, pressure is at 783 millimeters of mercury and Kelvin. I leave it to you for your instructor if they want you to change the units from what is given in the sample data, or if you're watching this as preparation for doing this in person, what units you choose to collect in and record on your data sheet. We are at 335 Kelvin, and our pressure is 797. And I think that's enough. So, hot plate off. If we waited, we could watch the temperature fall and see what happens to the pressure then. But that should be enough data for you, especially if you want to, again, switch over to XY. And then you could copy all of this data onto your data sheet, or copy every 30 seconds of data onto your data sheet. All right, so for the next part of the experiment, we're going to explore Charles's law, the relationship between volume and temperature. So I have a syringe here that the plunger moves relatively easily back and forth. It's a 60 milliliter syringe, and I'm going to set it to half of its volume at 30 milliliters. I have my vernier hooked up here, and it's measuring both pressure and temperature. Now, Charles's law is volume versus temperature, so we're not going to use the pressure sensor, but I wanted to have it hooked up just to show you that it stays relatively constant, so that we're only changing one variable at a time. I'll hook up the syringe to one of the ports on my Erlenmeyer flask, and the other port is hooked up to the pressure sensor. And it's at half the volume so that we can see qualitatively what happens when I immerse it in my hot water bath and in my ice bath. So my hot water bath is boiling, as you can probably see, and the temperature of the hot water, if you want to record it, is close to 100, but we're not quite there, at around 96 degrees, 97 degrees, 97.5 degrees. All right. And then let's see, qualitatively, what happens when we put our Erlenmeyer flask down in there. Hopefully the syringe won't shoot across the room. Is it not moving well enough? Our pressure is rising, so our pressure really needs to be at 1 atmosphere where it was. This is not any fun if I have to move it. It should move on its own. Just don't want it to blow up in my face. let it cool to room temperature and see what happens. The pressure inside the syringe was at 1 atmosphere. I don't think our syringe is moving well enough. Oh, yeah, there you go. You can see if I try and force it down, it goes back up. The air in here is at an elevated temperature still. As it cools to room temperature, let's see what happens. You can see right now the pressure is slightly above 1 atmosphere. The temperature is just sitting on the bench top here. We can't measure the temperature inside the syringe, but you can see it's bouncing back. But the volume has gone from 30 to 40 with the elevated temperature. Let's try it in the ice bath. The flask is still not really hot, but definitely warm to the touch. Put it in the ice bath, which, if you're curious, should be close to 0. Three degrees, 2.5 degrees. One and a half degrees. Let's see, the syringe isn't moving as freely as I would like, but let's see what happens if I touch it. See, if I squeeze it too far, it bounces back. But our volume now is 15. It went from 30 down to 15. Okay. So colder, the volume seems to have shrunk. Hotter, the volume seems to have increased. The exact volumes don't matter because we're not doing this super quantitatively. But the flask is definitely cold to the touch, and the syringe bounces back, and again, we're really, really close to 1 atmosphere, which is what we would expect because that's where we started. And I've let the syringe move freely by pressing on it, expand it, and it stays pretty consistently right around 15 milliliters at this cold temperature. See what happens as we warm it back up. I want to go straight into the hot water bath, just so you can see it again. Give it a whack. Once it gets a little more warmer. And I don't want to shoot the syringe in my face or potentially explode the flask. So I'll hold it in the steam. Immerse it in the water a little bit. See how it bounced up much higher that time? And higher still. And higher still. We're at 35 milliliters now. Our pressure, again, is holding right at 1 atmosphere. And as the gas in the syringe gets hotter and hotter, still right at 1 atmosphere. Ignore the temperature because the temperature was in the ice bath. Move it over to the hot water bath. Past 40 milliliters now, around 45, 42.5 or so milliliters. And our pressure is relatively constant at 1 atmosphere. Our temperature of our air in the flask should be the same as the temperature of the water in the beaker, which is really close to 100, since it is pretty much boiling. Charles's law, volume versus temperature. High temperature, we went from 30 up to about 45 at around 100 degrees. Ice bath, close to 0 degrees. Let it cool a little bit more towards room temperature. Again, the syringe is moving relatively freely and it's bouncing back, staying pretty close to 1 atmosphere. I go into the ice bath. And keeping it at 1 atmosphere, letting the gas expand and contract, move the syringe freely. At 1 atmosphere, at close to 0 degrees, we went back down to around 12.5 milliliters. Charles's law. And that's it. Hope you enjoyed.